Hey, hi everyone, welcome to this third day, first video of this TP workshop. If you are actually watching this one after watching all the previous things, I can guarantee you that you are among the top 10% people who are actually registered and are gonna be really good in TP because you have that willpower. So in this particular video, what we're gonna be talking about is unlocking more DP forms. Unlocking more DP forms means we're gonna learn more forms that can solve more variety of problems. So what we have talked about is this particular problem till now. Think about this one, this older problem where we were talking about, let's say, having a particular index over here, a level over here, right? And we were talking about having like something saved for the previous things based on problems. So based on the restrictions that we have, like less than equal to X time in total and less than equal to K slots in total, what we said was we would be keeping the whatever like information we need to check if we can take this item or not in the states, and we kind of decided that we'd be having something of the form DP of something, a restriction based form restriction and some form based things states over here, right? So this is what we kind of learned over here from the previous video. If you have not checked them out, obviously do check them out before this. So what we have actually learned is this form one, right? Which is going to be always DP of level. Like we have a level and you're iterating through objects. It need not be in this direction. You can even traverse in this direction. That's up to you how you want to model it up. But you're traversing in this particular direction and you are writing DP of level comma dash equal to something. Now this dash is going to get filled based on some partial information that you need to maintain for this things that you have taken, so that either you can decide what to do with this, can you take it or not, something in the check maybe, or this thing over here gets decided by whatever things might need to be might be needed to compute the answer. So maybe something you need to maintain as in, let's say, or zor or something of the numbers that you have taken or something like that. That can be a state parameter as well, something that you need to compute at the end. Okay, so this is something which we can kind of now comprehend because we have seen some problems of this particular format now. But this is not going to be complete for every problem. You might have heard about multiple other problems that are a bit different from them. So in fact, what we'll be doing today is we'll be talking about four more forms, and that is going to make your life much more easier, right? So what are forms is just a construct that I have created, or it's standard patterns only, but like I'm just going to give it proper names and I'm going to properly model them up for you so that you can think about them when it appears, you can recognize them and think in their own directions, right? How many are there? We have four more basic forms, and there are obviously at least three more medium hard forms that exist, and there are even more which needs to be practiced as you get very, very senior. But for now, we'll be doing four more. So in this particular video, we would be unlocking one more form, which is through this particular problem, that find the longest increasing subsequence of a given array, right? This is a very, very standard problem. In fact, today we will be taking more of a classical versions of the problems. I know that some of you might be saying, hey, Vivek, I already know these problems. Fine. Just understand these forms from the lens of these classical problems. We're going to get into non-classical problems and learn a lot of things from there too. Okay. So find the longest increasing subsequence of a given array. This is called the LIS problem. Okay, LIS problem, longest increasing subsequence problem. In this case, a subsequence, first of all, is anything that is like is a sequence which can be found out by deleting something and keeping the elements in order. So longest increasing, right? The element should strictly increase in the sequence. So we can kind of create maybe 2, 4, 5. I can take maybe 7, 8, 11. Sounds the best to me. This is something we can do. Find the longest increasing subsequence of a given array. And this is what we can keep over here, right? So this is what we are building. This is what we are interested in. So find the longest increasing subsequence of a given array. Maybe print it up, as we have already now learned how to print solution. That is now feasible to be done. But for this particular video, we're going to be focusing more on finding the length of this longest increasing subsequence, right? So this is the longest increasing subsequence: 2, 4, 5, 7, 8, 11. It's increasing in its value and it's longest of its length. You cannot find more than 6 in this case, I think, right? So how do we solve this particular thing? So let's try to solve this with form 1. So it's not like a particular problem can only be solved with one particular form. Let's try to see this one from its own lens. So we have certain numbers, right? Let's say in this case, I'm going to take 3, 2, 5, 4, 5. 3, 2, 5, 4, 5. So even in form 1, we can try to model this up. Let's say we have a level over here, right? and we can decide whether to take this in the subsequence or not. In order to decide if we can take this or not, we need to know what we had taken last, right? Because it has to be increasing. So maybe we can keep something like dp of which level you are at, okay? And what is the last taken, right? What is the last element taken in the subsequence? So from this particular state, because if you're taking something like if you have taken 5 last, then you cannot append 4 at the end of it, right? But if you have taken 2, then you can append it. Or if you have taken 3, then you can append it. So based on the what you have done in the last choices, whatever last element that has been taken, what is the best you can do from this particular part? What is the longest that you can do? So this is the basic form 1 like state that you can keep, right? This is the state part. If you have to design the transition, so this is the step 2. I think we're gonna follow the framework multiple number of times from now on. So if you have to write the transition for this, we're gonna be having dp of level. I'm gonna write level as L from now on because it's bigger to write. And what is the last value, right? From this, we can try to take this one in the subsequence. We can try don't take, okay? If you don't take whatever subsequence we had taken, whatever the elements you have taken in the subsequence, the last remains the same because you have not taken it. So we will try to do dp of level plus 1, L plus 1, comma, last. The last remains same. And if you want to take this one into the subsequence, the only check that is there is the current, let's call this array ARR. Okay. The check is actually ARR of current level should be bigger than the last. If this is true, then we can take this one into the subsequence, and in that case we will reach dp of level plus 1, right? And since we are taking this element now, if you're taking this for level plus 1, this is going to be this particular element is going to be the last element taken till now. Okay, so these are the two different places where you go, and this is what is the question over here: longest increasing subsequence. So this is going to return longest increasing subsequence in L till N with this as the last taken before it, right? So this is going to return me the longest increasing subsequence over here. Plus, since you are taking this element, this will be 1 plus this, okay? Because we are taking this particular element, so it will be 1 plus whatever best you can do from going forward. This is the best you can do even till this much. Best you can do over here plus this one will be the best you can do with this one. This is what we will have. Out of these two, whatever is the maximum length, we will take that one, and that is what is going to give us a dp. So this is going to be the transition, and this is actually like a perfectly possible solution. I mean, I think people feel that you know only like if you already know the Elias problem, you know only a classical version, but every form can kind of give you some variation to it, maybe, right? For certain kind of problems, it is possible that it can be solved with form 1 and form 2, both. So transition over here is this max of these two, right? Let's quickly do the time limit check as well. What is TL check, or what is the number of states? The number of states would be equal to now L level, the length of the array, N, right? Let's say the length number of elements is N, right? Comma last, what is the last element taken? Now over here we can store the last element that is taken value, so it will be multiplied by the amount of values that is possible, max value, or I would say max of ARR. Okay, this is the number of states because everything is feasible, and number of transitions is going to be just 2, right? So if you use that formula, we will get an order of N into max of ARR as a solution, right? So this is one particular possible time complexity. Another thing that we can notice, this is a very, very good idea. Try to keep this in mind. When in a lot of problems, you have to keep the last, right? And in a lot of times, this last is obviously a value. It's a value, right? We are comparing it with the last, but we can also try to keep the last index that we have taken, right? At times, this last is going to be a value, but that value is going to come from the array itself, right? So what we can do is we can keep the index that you had taken last. That is another option. In that case, we will not compare with last, we will compare ARR of last. Okay. So we can change the meaning of the states as well. This was level and this was the last element taken, but we were saving the value in the parameter. Now we are saving the index of the value that is there in parameter, because the values in the array can be pretty large, but indexes are finite, right? It's up till N only. So in that case, if you use last as let's say index, Okay, then in that case, number of states is going to be equal to n into last is an index, so it can be up till n only, which is order n square, which is order n square, and we have number of transitions as 2 still, so this will give you an order n square solution. Okay, so this is a order n square solution that you can do, where you maintain dp of current item and what is the last index that you had taken in the subsequence if you maintain these two things. So this is form 1 solution for this particular thing. I'm not going ahead and coding this one because we have, I think, coded some form 1 questions already. In case you have this doubt, maybe you can ask me up in the doubt session. I will code it up for you. It's very straightforward, much simpler than the previous problems that we have coded in the live sessions, right? So that's there for the form 1 formulation, but we are not over here to learn form 1, right? Let's get into form 2 and try to learn form 2 from this one. Okay, so let's talk about form 2 now. So form 2 is a bit different from form 1. It kind of has this index and configuration itself, and what we're gonna have is like what is the current state. You can have the full state configuration over here as well, but what I would say that it's mostly index, right? You will have an index, and what you will do as a there would be some extra parameters over here depending upon what you need to maintain, just like other problems. Like if you have certain constraint in the problem, you might keep something over here that would help you decide if you can do something or not. But what generally this is going to return is not what is asked in the problem for the full solution over here. It's going to return what is the best, whatever is asked, ending at index. Okay, whatever is asked in the problem, what is the best of that ending at this particular index. So what do we have? Like if you're processing just this much from the start to end, okay, if you're processing this much from start to end, what is the best answer, whatever thing you want to maintain, ending strictly at this index, like that particular subsequence, that particular substring, whatever it is, should end at this index. Like that means it should include this index in its whole composition, right? So this is the setup for form 2, and I generally term this as ending form, right? Ending form. I mean, it can equally be like starting at this till end. You can do it the other way around, but I call it as an ending form because I mostly solve these problems in like keeping it like the best solution ending at this particular place. And this is what is used in a lot of problems. We're going to see more examples as quickly as well after this one. But let's quickly go back to the problem that we had and try to solve it with like form 2. So let's say we are given a certain array and we need to find the li. So we have a1, a2, a3 up till an. Okay. So what we'll do is we will first of all, we know it's form 2. So now we will start with the second phase of the framework, that is write the state definition. Okay. And the standard template that we will follow for form 2 is dp of, again, the level, okay, level, comma, whatever is required to maintain the solution, equal to best longest increasing subsequence, whatever was asked, ending at level, okay, ending at a particular index. So let's say there is something over here. What is the best one ending at this particular place, at this element? That's what we want to find. In, you can say, obviously, like if it's ending over there, it has to be in the part 1 till level, right? This is how we maintain this particular thing. This is what we keep as a dp. And in this problem, we don't really need to keep anything as a parameter for this problem, like for LIS problem. So we'll say dp of level would be equal to best LIS, longest increasing subsequence, ending at this level. Okay. For an example, let's take a quick setup. Let's say 2, 1, 5, 3, 6. Okay. So in this case, the best longest increasing subsequence ending at this particular index, dp of this index, like one, let's call this 0, 1, 2, 3, 4. dp of this index, okay, of 0 is going to be equal to 1 because it has just a single element in it. The longest increasing subsequence ending at this index is also 1, okay, because the best you can end over here is 1 of 1 length, just this single element, because you have to take this element. It is mandatory ending at this level. At 5, the best you can do is 2 because you can take any 2 sequence and just keep it like this, right? For 3, we can do 2 as well because we can take these 2 elements and do over here. For 6, we can do 3 because we can take, let's say, some sequence like this 2 3 2 3 6, and you can do 3 over here. So the numbers saved over here means the best subsequence, longest increasing subsequence ending at this index. Now note that if you, let's suppose, get a 2 over here, okay, 2 over here, the best subsequence ending at this 2 is nothing but 1 followed by a 2. So the answer over here would be 2 and not 3, because even though we have found a better answer in before, the one ending over here, the best we can do is 2. So that's the meaning of this particular DP. Best, whatever is asked, LIS in this problem, ending at this particular index, okay? Or count of, or best, max, min, whatever is asked in the problem accordingly, okay? And this is the state definition. Let's move forward and try to think how do we design the transition. So I'm gonna like move down and try to write down the transition. Okay, the way the transition works in these things is you loop over the previous level by which you can extend and build the solution. Okay, so let's say you have 2 1 5 3 6 2, right? So when you're considering, let's say, this as the level, let's say this is the level, okay, or let's first start with this as the level. Okay, what is the best subsequence ending at this thing? Now note that like it's a recursive function, so we know that we can call it for previous levels too, right? The way this works is we try to find out, okay, there are certain numbers, there is a subsequence which ends of length 1 at 2, there is a longest increasing subsequence of some length, that is equal to 1, which ends at 1. There is a longest increasing subsequence of length 2 which ends at 5, which is nothing but 2, 5 or 1, 5, any one of them. The length is 2. Now to find out what is the best length at 3, the way it is, like, if there is a subsequence of some length, x length, right? Either that can be 1, just this element, okay, or there has to be some element before it, and then you immediately after that there is a 3, right? Like if it is a subsequence, there has to be some element and followed by a 3, because there has to be some element before this, right? So we will find out which element can that be. We will loop over the potential value of the immediate last. So this, it is ending at this value. What is the element which is last but 1 in the whole sequence or subsequence that we are forming? Okay. So in this case, it can try and extend like whatever was formed till 5 and then extend it over here. It can try extending this over here. It can try extending this over here. But what we realize is that if there is a subsequence which ends at 5, like let's say 2, 5, we cannot extend 3 at the end of it, because the last value 5 is bigger than 3. So it will be 2, 3, 2, 5, 3, which is not a increasing subsequence, right? So that the sequence is increasing, the last ending that you're extending should have been greater value. So we extend it only when the previous value is smaller than 3. So that's the main transition. In fact, for 6 also, like you can see that we can try and find out the best extension that is possible. It will come from, let's say, this one itself, or maybe this one, and any one of them. But the main transition that we write for this is dp of level, okay, is equal to max of dp of some pre-level. I mean, I would say just previous level, or I will not say level, previous taken, some previous taken element plus 1, because there is some subsequence which ends at a previous taken element, and then you are adding this current element at the back of it, the immediate previous, okay? And since that element has to be like dp previous taken, the previous taken can be one of the indexes in the from less than level. So this is the index, right? Level is an index, has to be up till, let's say, index number 0, right? 0 till level, it has to be one of the indexes. That's the definition by default. And the next thing that has to happen is the element ARR of previous level, previous taken element, has to be less than ARR of level. If this is possible, then only whatever was ending at this previous taken, we can extend it by adding the level at the back of it. So if these two conditions are satisfied for a previous level, then only we take the max across all such previous levels and we will get the answer. Okay. So this is the main transition for this particular code. Okay, this particular problem. Does this make sense? No? Yes, right. We have things going back. So we find out what is the previous element and then we loop or find out that. We will loop over the previous element taken. So it is like loop over all these elements, and only if this is valid, then we will try to take a max across it. So let's try to find out the time complexity, and I will show coding it as well. So let's say time complexity or complexity calculation. Let's put this one. Let's go and count on complexity. What is the complexity for this particular problem? Think about it. I think I have already given you guys the formula, so you guys can anyways find this out. So number of states, the level can take n values. Number of state is n, right? Number of transitions, we need to find out the maximum, right? So maximum can take anything in the 0 to level, and level can be up till n. So we have to loop over all the values. So even if you loop, it is fine, and because it can be potential solution. On the worst case, everything can extend. So on the worst case, the number of transitions is going to be n as well. Okay. On the worst case, the transition is n as well. So now you can see that the transition is not 1. In most of the previous problems that we have seen till now, the transitions were 1 or 2 or 3, something like that. In this case, it's n. So in this case, the time complexity will come out to be s, you can say n into 1 plus n, the formula, number of s into 1 plus number of t's. Though it's not number of t's, it's average number of cost for t's, but yeah, we will see it this way itself. Order of this, and it's nothing but equal to order n square. Right? So we have an order n square solution in this way as well. So this is the time complexity of this. Let's quickly see how to code a problem of like form 2, just so that you are clear on this form 2 as well. So let's see, let's pick out this one. Over here we have, let's say we are gonna be given the integer n and the ARR, integer ARR, like up till whatever value you have. Let's take it. See in n integer ARR. Okay, for integer I equal to 0, I is less than n, I plus plus, C in ARR of I, right? We are taking the array values that is there given to us. And now what we're going to be doing is we're going to be finding out the LIS. So we're going to write the recurrence, integer recurrence and integer level. But in this case, this is going to return best LIS ending at level. This is what we're going to finding out over here. So again, we're going to write the same thing. We're going to have the same framework, pruning. What do we have more? We have the base case. Then we have the cache check. Then we have the, what do we have? Compute, save and return. Right, this is the 4 things that we have. Now for pruning, we can keep anything as such, doesn't really matter. When you're finding out the pruning, maybe I can keep if level is less than 0, we can return 0 length. That's feasible, right? Also maybe like even like this can work as a pruning and as a base case. Like maybe if something is less than 0, then it doesn't really make sense. Yeah, this is something we can keep as a pruning. Like if its level is less than 0, it doesn't really end at that index. Or if level is greater than equal to n, you can keep this as well, but we will never access that, so it doesn't really bother us. Next is we have some base case. In true sense, we don't really need any base case as such, because in this case we are checking everything, and if nothing is working, we always have a default value of 1. So the base case is gonna be like integer. We don't really have a base case as such. This can behave as a base case, so we're gonna have that separately. To compute, we will have an answer equal to 1 by default. Okay, and what we'll do is we will find out the previous taken in the range 1 comma equal to 0. Previous taken is less than the current level, because previous element has to be before that this element. It cannot be like on this element again. Previous taken plus plus, and answer equal to, you can have max of the current answer, which is by default max 1 is always possible in this question if you can take this element. Okay, if ARR of previous taken element is bigger than, is lesser than ARR of the current level, then what we're going to do is we're going to find out answer equal to max of answer plus, if you take this element 1 plus whatever was best ending at the previous taken element. So DP, that is going to be recurrence of previous taken itself, right? That's there. So for like we don't really need to write a base case, because for the first element we will not even loop, right? So it will get its value from there itself. The default value 1 will be returned, right? So this is the whole recurrence, and if you return just answer over here, you're good to go with the whole recurrence as such for solving this problem. That what is the best ending at this particular I, you're good to go. But obviously we are writing DP, so we will write DP of 101. So I'm just keeping a default higher value. You can keep anything as per the problem. Base case is not required. Cache check if DP of level is not equal to -1, return DP of level. In this case, -1 is never accessed because length is always positive. In this case 0 or at least 1 is always possible. So in this case we can maintain DP with -1, so we can do memset DP -1 size of DP. We set all of the elements to -1, and then what we do is we have this recurrence ready. So as soon as you flush, you think about, okay, now I have computed, like I have this function and it is anyways going to cost me order s into t1 plus t, the formula that we have already written down, right? So this is the full thing. The only thing that is left is to save before we return. So I'm gonna just do this, DP of level equal to this. So save before you return, right? So that's the whole DP code. We don't really need a base case. So this is like first function which doesn't really need a base case, because the transitions are gonna stop at some point in time, and that's gonna behave like a base case on its own, right? So that's the like full DP code. Now there is one small caveat. The recurrence doesn't really return us the best alias. It finds out the alias ending at I. Now the best alias, whatever is possible in the whole array, has to end at one of the indexes. So what we'll do is we will loop over all the indexes for integer I equal to 0, I is less than n, I plus plus, right? And we will maintain integer best equal to, let's say, 0 possible length, which is not the case. We always have something possible if the array is non-empty. So in this case, what we'll do is best equal to max of best comma whatever best you can create at this index. So whatever is the longest increasing subsequence ending at this I, take a max of all of them, and that is the like alias that you can print over here, because whatever is the longest increasing subsequence is going to end at some index, right? And so it will be possible to get it from one of the recurrences of I. So if you loop over all of them and find out the best one, you're good to go. Okay, so that's the whole setup of this code, and in fact this is going to give you the whole alias. And as we talked about things, the transition over here is order n and the state is order n, so it total is order n square. So with form 1, form 2, we could solve both of these problems, right? So that's the whole code for this one, and this is mostly how the codes generally sometimes look for subsequence problems. So generally these subsequence problems and some subset generation problems sometimes happens to be form 2. So because you're extending, that's a natural thought process, right? You're extending something. So this is how form 2 kind of works. This is like one problem. We have solved alias now in n square. Though if you want to think about it, can we do better than this for alias? It turns out yes, we will learn that up in this particular series as well, because n log n alias is also possible, and it's a very standard technique. I will talk about that in the next day. But for today, let's focus on one more problem of this form 2. Okay, let's get into that. So another problem that we're going to take on form 2 is this one, which is very classical. Find the maximum sum path from 1,1 to n cross m if down and right moves are only allowed, and you are given a 2D matrix which is going to contain values, right? So it's like you are at this particular cell and you need to reach this cell. You can go down or you can go right. Okay, and these values are the values that are like kind of there at each cell. And if you take a particular path over here, let's say like something like this, so you're going to get the value sum 2 plus 3 plus 1 plus 5 plus -3 plus 2 plus 3, right? So this is possible, and we need to find out the maximum such sum path. So in this case, can you find it out the maximum one? Let me try to find it out as well. In this case, I think one is like this option. Okay, one I can feel is this option. In this case, we're gonna get 2 plus 9 plus 5 plus 5 plus 11 plus 5 plus 3. Essentially, it's gonna be 9 plus 11 is gonna be 20. This is gonna be 10. This is gonna be 5, and this is going to be again 5 plus 3 as 10. So we have around 40. Okay, and in this side we can see that this is already 10, 10% 20, 20 plus 11 is 31, and then this is around 5. So this is lesser, right? But 36. So we get a better path on this side. So in this case, the final answer is going to be equal to, like, the final best path is going to be equal to this one over here. This is the best possible path. Okay, and I don't think I can find any better than this one on the grid right now. Okay, so this is the best path. You have to find out the maximum sum that you can make using a path from going from this side to this side, and note that I can only go down and right. Okay, I cannot go it this way. This is not feasible. I cannot go this way. So this is another classical problem, and the way we're gonna see this is again from the lens of ending form 2. So when any particular person is kind of moving, or the path is moving, it's gonna be, let's say we can try to trace it like a person is kind of moving in the path, and at any point in time, if the person is over here, right, we can try to see that, okay, it's actually a path ending at this configuration, right, that the person is over here. So when you have a path, it's like you can trace the path and take the configuration is like each cell right inside the path. So we're gonna say a very similar thing to form 2 that we have discussed for Elias over here as well, that this is going to be my config. Okay, that this is my configuration at which I am currently at, and then I will say, okay, dp of this configuration is going to be returning me what is the best path ending at this particular point. What is the best way in which you can reach this cell? That's what we want to find. In fact, if you just call out dp of this cell, you will get the answer, because that's the best path to end over here. So let's try to formulate it with form 2 again, and I'm gonna like kind of quickly go through this one. This is very simpler compared to the last one if you're already knowing form 2 now. So the way we'll do is like, we know it's form 2, so the second step is to find out the state. The way we'll do it is dp of configuration. Now a particular configuration in this case is a cell, right? So cell can be kind of mentioned with 2 parameters, which is its row number and column number. So let's say r comma c. Okay, dp of r comma c, and which is the current cell whose configuration you want to find, like reaching that cell. So, and it's going to return best path, best, in this case, max sum path ending at r comma c, starting from 1 comma 1. I mean, every path starts from 1 comma 1, right? It's given in the problem that you have to start from 1 comma 1 and comma 1. Okay, this is the state that we'll keep for this problem. Best ending at this configuration, and it has to be best. Okay, now let's try to find out the transition for this one. Very simple if you understand the path logic. How can you reach this config? What was the immediate last track, like transition or actions that you could have taken, and where could you come here from? In the last problem, we said that this element could be the end of Elias if you extend from somewhere over here. So we iterate over the last ending. Very similarly, in this case also, if you are over here, the way you could have come from this side or from this side, right? It's either you come from this side or you come from this side, right? So when you are at a dp of r comma c, okay, the two ways is you come from this side, or the other ways you come from down. Okay, you made the last step as down and you came to over here, you came from this cell, or you made a right and you came from this cell. That's the only two options that we have, right? Provided that these cells exist. Like if you're over here, then you cannot come from right. Okay, so if these two exist, I mean, if r is not equal to, let's say, 0, like if the column is not equal to 0, then we can come from right, and if r is not equal to 0, then we can come from up as well. And in this case, what we're gonna do is, what is the best that you can do from over here? And in this case, if you come from this side, the value that you're gonna get is whatever best you could, the best way you could reach dp of. So if this is r comma c, this is going to be r comma c minus 1, and this cell is going to be equal to r minus 1 comma c. That's how rows are there. This is row, this is column. So column decreases by 1. So over here, we're gonna write dp of r comma c minus 1. We came to this cell, okay, r comma c minus 1, and then one step over here. So when you make the one step, you're gonna get the value of at this particular cell, okay, plus arr of r comma c. That's the value that you get. Whatever best value you could make by ending over here, plus you extend it by one more step. Let's think about one more, the other side of the transition. dp of r minus 1 comma c, you come from the cell above, whatever the best way was there to reach over there, plus arr of r comma c. Okay, these are the two transitions, and we want to find out the maximum best way to reach over here, so we were going to take the max over here. Okay, that's in fact the whole transition for this particular problem. Okay, now if you quickly go ahead and try to do a time limit computation for this one, like what is the time complexity, that's also very, very straightforward if you think about it properly. Over here we have a state which is r comma c. R can take n cross m, so the configuration is nothing but row and comma cell. So if the dimensions of the matrix is n comma m, we will get number of states as equal to order n into m. Okay, and number of transitions in this case, average number of transitions is 2, because only 2 ways you can come to this cell, right? 2. So again, the formula, if you put this into the formula that we have talked about, n into m into 1 plus 2, order notation of this, which is going to be equal to order n into m. So that's the complexity of this particular DP solution. Okay, and now since we are done with this particular DP complexity check, we can go ahead and code it up. So we'll do quickly the same thing again. So as you can see that for every problem we are using the same formulation, right? So this is the last LIS problem that we coded. I'm gonna just quickly maybe start from scratch itself. It's not gonna take me much time, I think. Maybe for you it is gonna take some time. So we're gonna take the n, m that is there in the question, and then maybe the whole matrix is given to us in the question as an input. Okay, so that's the whole thing, and now we're gonna be using the recurrence. So I'm gonna write the integer recurrence, the best way to end I at row at c. Okay, this is like any configuration that you need to keep over here. It can be index for a linear array, it can be cell number for a 2D array. So now this is over here. Now what we're gonna do is this means the best path sum ending at this one. We're gonna write the pruning. Pruning can be like if r is less than 0 or c is less than 0. In that case, these are not possible. Okay, so that's one option. So if this is the pruning and if it's not possible, what do we return in this case? That's my question. A really interesting question. If you cannot go at a particular cell, what can you return? I mean, if this is an invalid state, what do you return? So this is pruning. So in case since this is a maximization problem, if you return minus infinity over here, then it's gonna be like making the max go to the other branch. So let's see. I'm gonna fill this value over here, but let's first fill out the rest of the things. Let's fill out the base case. So when you are at 1, 1, we will have our base case, right? If r equal to 0 and 0, 0, c equal to 0. If you're at the starting cell, then that's the base case, because that's where we will start, right? In that case, we will return arr of 0, 0, because if you're starting over there, you're gonna get that value, right? So that's the value that we'll return. Or else we will compute the answer, integer answer equal to, we will have the compute step, answer equal to max of answer comma max of, there are two different transitions, I'm directly writing it over here. Recurrence of r minus 1, you can come from r minus 1 comma c comma plus arr of r comma c, or you can come from recurrence of r comma c minus 1 and you get plus arr of r comma c. These are the two options that we have. You take the max across that, and that is what is your answer, and you save and return. You return answer, right? That's the whole transition, like recurrence for this particular problem. And now note that if I return over here, return something like a big negative number, minus 1e9. Okay, so in that case, this will become very, like when you, let's say the r is equal to 0 and you're calling r minus 1, this is invalid. So it will return huge negative value. Huge negative value for plus any particular value is going to give you a positive value. Sorry, a huge negative value. So the max will go always into this branch, which means it will only take the branch that is feasible. So this is how you can do prunings for maximization problems where you return minus infinity. Now what happens if like things go problematic and you don't really seem to find out any possible value which you can return, because values can be 1e9 as well. maybe you can make it long and make a very big value returned over here. The other way would be to just simply add a check over here, like if integer answer equal to 0, if let's say if you're at this cell, you're obviously going to get the value over here. If r is not equal to 0, then we can come from the other side, answer equal to max of answer, comma this part, and I'm gonna just quickly copy this up, paste it over here. If c is not equal to 0, then we can come from the top as well, and this is the path for that. Whatever is max across all of them, we're gonna return, and like either of them has to be true, so I'm just gonna keep it 0 for now because rest all will be handled directly. And what we would be doing over here is, like, keeping 0 over here is correct. It's not wise to keep -1 over here. Okay. In fact, since it's a maximization problem, it has to be either of these two. So you should ideally keep 1e9 over here, -1e9 over here, because whatever is a positive, like bigger number, it will kind of take that. 0 is even not also correct. Maybe the path value is negative. What if the cells contain all negative values and the sum is going to come out some negative value? So if you keep a 0 over here, that's wrong. Very, very interesting point. If you keep default value over here as 0, that would be wrong. For a maximization problem, default values are going to be -infinity. For minimization, +infinity. For counting problem, 0. Okay, that's over here, and then you return the maximum answer that is saved over here. Now, this is the whole like recurrence for this one. I think this should give us the answer. Like if you print cout, let's say, what is this? Recurrence of n-1, m-1. That's the last cell in the grid. It is going to give you the answer. But we obviously need to add a DP to this. The first thing that we can do is we can simply cache and like do the standard stuff, like create a DP array, and the way we do it is we add a save and check. We're gonna do if DP of r comma c is not equal to -1, so we can return DP of r comma c, right? And the other thing that we can do is we need to make sure that whatever we are returning, we save it in the DP array. So this is what we can do. But there is a small problem that happens due to this. Note that the cell values in the grid could have been negative. Like in the previous case, you could see that cell values could be negative over here, right? So what we are kind of dealing with over here is maybe the returned value from the recurrence itself is -1. What if this answer is -1? In that case, you will save it over here and it will kind of check it again and again, right? Because it's -1, so it will compute it again. But the actual value is -1. It's not like the previous value is -1, right? It is not computed. It's more about its actual value is -1. And since it's like the values could be pretty much anything, I don't know how to maybe check that. So this is something we even talked about in the last doubt session. Somebody was asking about this one. What we do in this cases is we keep a boolean. Is this state done? Is this state calculated yet? 0 or 1. That's what we're going to keep over here as well. So if this state is not, if this state is done, okay, if this state is done, then we're going to return this particular thing. Okay. By default, like every state, we are anyways looping over here. So I'm going to keep done of I comma j as 0 because it's not done. Any state is not computed yet. And if it's done, we're going to return the saved value. If it is not done, we'll compute it. We will return the like correct value. But before that, we need to make sure that, okay, if it is not computed, then we'll compute it and mark it done, that it's marked done. And we have saved the correct value and then we have returned the correct value. Next time when it will come over here, it will return the correct value. So this is independent of any saved value in the DP array itself to decide what has been computed and what has not been. So this is actually the perfect way to kind of do the DP problems. But since we can get away with many problems in using a single array, DP array with -1 and some other values as the correct values, we do that. But this is actually the correct way to kind of keep track of which has been saved or not. Okay. So that's almost all for this particular problem. If you we have set the done, so just set the done array as 0, and then if you just call this recurrence, it will give you the correct value. Okay. So that's almost all for form 2. Okay. So this is all for form 2. So the key idea is if you see any particular problem with certain path, sequence, sub arrays sometimes as well, dependencies where like the next element has to depend upon what you have taken previously and there is like a direct one-to-one relation between them, then maybe it's a form 2 problem. Okay, that's a key indicator that this might be a form 2 problem. Okay, so in the next video we're going to unlock more and more forms. So this is that all about this particular video. See you in the next one. We will talk about form 3 in that one. Okay, so see you there. Bye bye.